start to talk about Dirac theory. It has to do with 2.5 particles. And so the way we introduce this idea is following the original idea by Dirac, that we wanted to have relativistic quantum mechanics, which means we need probability interpretation. Which requires that the equation is first order in time, just like the Schrödinger equation. But at the same time, we wanted to keep space and time on equal footing because we wanted to have relativistic equation, which then requires that this Hamiltonian has to be also first order in spatial derivative. So this is basically energy, that is the time component or the Paul vector. When you want to make sure that it is relativistic and the length invariant, if this part is the first order equation in time, this part also needs to be first order equation in space. And first order derivative in space is the momentum in quantum mechanics. So we need to have something here which is linear in momentum. So that requires us to write an equation which is first order in momentum. And because momentum is a vector, we need to contract this the spatial index with something else. We didn't know what it was, so we introduced this alpha, which is unknown at this stage. We also need contribution from mc squared to energy. And again, we don't know what it multiplies, so we introduced this beta in here. So this was the equation. And of course, when you have a stationary state, this is supposed to be the energy, so that was the argument. And then we just go ahead and square this to see if we can reproduce the correct equation for the relativistic energies. So we're going to make sure that we reproduce this. So when you square this, you have this thing squared. And make sure that this actually equals this one. So we just expand this square, c squared, alpha I, pi, alpha j, pj, summed over both I and j, so this is alpha dot p. We have the cross term. And then you have the last term squared. The whole thing multiplying sum. And to make sure that this is the same as the relativistic energy squared, we can then find the following on what alpha and beta should be. This one is easy. This should equal m squared c to the fourth. So we find beta squared is 1. Here, I have cross term between p and mc squared. In this term, the order is alpha times beta. In this term, the order is beta times alpha. And we shouldn't have a term like this in here. So what this means is that alpha and beta should anti-commute. Then this term and that term cancel against each other. Finally, this piece here is supposed to be p squared. I wrote it in a suggestive way. In order for this to be true, then I can do the following trick. I have alpha I, alpha j, pi, pj. So I move pi over here. Two p's are the same thing. So this is already symmetrized between I and j indices. So instead of writing alpha I, alpha j, I can also symmetrize I and j indices and make it a half, so that that stays the same as the original one. And this thing has to equal pi. So what that means is that alpha I, alpha j has to be 2 delta ij. Then this piece recovers c squared p squared. So in order for Dirac's idea to work, alpha and beta are clearly not simple numbers, but they are something else. And in the end, this actually turns into matrices. So that's the argument I have given to you on Wednesday. Any questions about this line of arguments? Yes, Alessandro.
Can you please further explain why we have the term with the mass, like the mc square beta?
This one?
Yes, exactly.
Because we really do need to have the m squared c to the fourth inside e squared, right?
Just for that? Okay.
Yeah.
Okay.
And it also qualifies because everything has the correct dimension. This is energy. P times c has dimension of energy, and mc squared, as you know, has dimension of energy. So, so you're putting basically everything you can think of linearly together, and so that it produces the correct dispersion relation between energy and momentum.
Okay. Thank you.
Anything else? Okay. So what could this be then? So I already wrote this on Wednesday, but let me just repeat it. If you define matrices defined this way, and they are all 4x4 matrices, then this is written in 2x2 block diagonal form. So the notation here is that when I look at alpha 1, for example, it's the Pauli matrix sigma 1. So this is actually meant to be 0 for the upper left 2x2 block. Upper right 2x2 block is sigma 1, which is 0, 1, 1, 0, right? Lower left 2x2 block is also sigma 1, so that's this sigma 1 Pauli matrix. And lower right, the 2x2 block is all 0. So this is the notation. So whenever you see sigma here, you look at this block and that block and put in the 2x2 Pauli matrices in there. And beta being 1 minus 1 is also in the same notation. So what's meant by this is that this one is meant to be 2x2 identity matrix. This is also identity matrix but with minus sign. And upper left, right, and lower left blocks are just 0. So that's the notation. And then we can verify these requirements over there. So beta squared is easy. So this just turns into 1 squared minus 1 squared. That's 1, 1. So that's exactly what we need. Beta squared is 1. This anti-commutation between alpha and beta. So alpha and beta anti-commutator. So we just go ahead and multiply them. So this is 0. This is minus sigma I. This is sigma I. This times that is 0. Plus, this times that is 0 again. This is sigma I. And this is minus sigma I. This is 0 plus 0. Now you see they cancel with each other. So this is indeed 0. So that satisfies this requirement over here. The last one is the anti-commutator between alpha. For this one, we actually remember the Pauli matrices also satisfy a similar relationship which you may or may not remember from quantum mechanics. So if two sigmas are the same, sigma squared is 1, 1 plus 1 is 2. If you're looking at two different Pauli matrices, like sigma 1 and sigma 2, sigma 1 plus sigma 2 in general ij. So sigma 1, sigma 2 is given by I sigma 3. This is totally antisymmetric. And if you add them, this is ij plus ji, given that epsilon ijk is totally antisymmetric, then they cancel. So that's how you get 0 when I and j are different from each other. So alpha I, alpha j is just a 4x4 version of the same thing. So this is definition. When you multiply them, this is sigma I, sigma j. This is the opposite order. And if you sum them, each 2 by 2 block, turn into this anti-commutators. We have learned that this is 2 delta ij. So this is 2 delta ij times identity matrix. That's this requirement. And you can prove that 4x4 matrix is the minimum size to satisfy its relationships. There's nothing smaller than these to satisfy these requirements. So that's how Dirac came up with this equation. Any questions about these matrices? Yes?
Do they have to, are they unique? So the alpha and the beta?
So that you can also show that they are unique up to unitary transformation.
Okay.
Namely that if you do a basis change of the notation for psi, by some unitary matrix U, you can also transform these matrices this way, then everything remains the same. So alpha and beta are unique up to this overall unitary transformation that corresponds to basis change. That's an excellent question. We actually come back and use that fact later on. Any other questions? Yes, Kate.
How did we observe that this is a two-level system? Like this is spin half?
Yeah, so we will actually talk about why this is going to happen in a moment.
Okay.
Okay, so this was meant to be the quantum mechanics. So let's see how far we can go with that idea. So, all we got, this is meant to be Hamiltonian. Now Hamiltonian is written this way. Then we can ask the question, what is the conserved angular momentum or momentum? For example, we can see immediately the momentum commutes with the Hamiltonian, because momentum commutes with the momentum itself. This is not a matrix, so it commutes with all of this alpha and beta. MC squared is just a number. So Hamiltonian conserves the momentum, that makes sense. For a free particle, momentum is supposed to be conserved. Then next question you ask is the angular momentum. So this obviously is the orbital angular momentum. Now you see that they may not commute because P commutes with P, but X doesn't. So XP gives you IH bar, so it doesn't commute. So if you actually work this out, you'll find So now you have to think, okay, this Hamiltonian doesn't conserve angular momentum. But of course, we know that if the system is rotationally invariant, and it looks like it is because all the spatial indices are summed over here, then there must be conserved angular momentum. But what we see here is that orbital angular momentum by itself is not conserved. That's where we come back to case question. Perhaps we should add spin to this. So that we can find a conserved angular momentum. And the question is, what could S be? And we can do trial and error, but to save time, I'm going to give you the answer right away. So S, spin angular momentum, is given by also a matrix by this capital sigma. And capital sigma is defined by simply, again, 4x4 generalization of the Pauli matrices. So if you just look at the 2x2 piece here, Pauli matrix times h over 2 is the familiar expression we have in quantum mechanics for spin 1/2. So that's the spin matrix. And when you go ahead, actually compute this commutator, you have sigma here, and alpha also have the sigma matrices in there. So when you actually compute the commutator, lo and behold, you find this contribution. So if you sum L, orbital angular momentum, and spin angular momentum, where spin angular momentum is defined this way, then this commutator and that commutator precisely cancel. And then you find that this J is indeed conserved. It commutes with the Hamiltonian. And clearly, if you look at the eigenvalue of this spin matrix, for example, Z component, and again, this is a 2x2 block notation, so this is sigma Z for upper left block, -1. Sigma Z for the lower right, 2x2 block. Everything else is 0. So this is already a diagonal matrix with the eigenvalues plus minus h over 2 as eigenvalues. So that's clearly spin 1/2 particle. So that's how we know that Dirac equation, he came up with this argument of trying to achieve the rhythms of quantum mechanics really does give you spin 1/2 particles. Any questions about this? Yes?
What if you represent those relations on like a larger vector space? So
Can you do that again?
what if you have like larger matrices satisfying those relations?
So it turns out that,
a bigger spin.
yeah, the larger matrices actually, if you want to do this, turns out to be just multiple copy of the same thing. For example, if you want to have 8x8 matrices, you put in these alphas this way. This is 4x4, this is 4x4, and then you have 8x8 matrices, and then they satisfy the same requirements, so that qualifies, but it's just that you get 2 copies of the same thing. So it turns out that any way of getting these relationships satisfied is the 4x4 block is the minimum. And you can go bigger, but the going bigger only means that you get this 4x4 thing multiple times. And so in mathematics language, that's called reducible. This 4x4 thing is irreducible, so that the smallest thing you can write, but the only thing you can do more is to get multiple copies of the same thing over and over again, up to the unitary equivalence we talked about just a minute ago. So in that sense, it is unique.
It'll always be spin 1/2.
Yes, because once you actually get multiple copies, you just get this also matrix multiple times. The eigenvalue is always given by the same plus minus h over 2. Thanks for the question. Anything else? Is that good? So far, so good. Looks great, right? You get something that seems to allow for the probability interpretation because it's the first order equation in time. Space and time seems to be treated on equal footing. It's relativistic. You did recover the correct relationship between energy and momentum. That's quite non-trivial. And somehow automatically you got spin 1/2. We didn't impose it, but somehow spin 1/2 came out. So that even led to the conjecture by Dirac that in order to combine quantum mechanics and relativity, this is the only thing he could come up with. It looks all right. That predicted spin 1/2. So nature has to be made of only spin 1/2 particles. Well, that's a little extreme because we know photon is spin 1, but probably he meant that maybe photon is a composite object made of two massless spin 1/2 objects. So that was at least his conjecture. And it's actually even better than that. This Dirac equation also predicts G factor of electron is 2. And if you remember in quantum mechanics class, magnetic moment E of an electron is given by this Bohr magneton times spin times the G factor, and you get told the G factor is supposed to be 2. And there was no reason why. This is basically what experiments tell you, that G factor is supposed to be 2. But with Dirac equation, you can derive G factor is 2. So let's try that. In order to do this, we take non-relativistic limit of Dirac equation. So we simply just write out this equation. So this is alpha dot PC. So this is MC squared beta. And in the non-relativistic limit, MC squared is a big number, and C times momentum is a small number. So this is small, this is big. Then we can do the second order perturbation theory, just like what you do in quantum mechanics. So you can say at the first order, this is MC squared. So you take this big one. But the second order perturbation theory, you use this off diagonal piece that brings the upper component to the lower component. Lower component has zeroth order energy, which differs from the original one by negative 2mc squared. That's the energy denominator. And from the lower component, you come back to the upper component like this. This is sigma, sorry, not alpha. So that would be the contribution at the second order perturbation theory, like what do you normally do in quantum mechanics, right? If you do that, C cancels mc squared. Sigma p is sigma I pi sigma j pj. Once again, p and I are symmetric. So I can turn this into anti-commutator with a factor of a half. We learned that it's 2 delta ij times a half, that's delta ij. So this is pi, that's p squared. So sigma p times sigma p is p squared over 2m. And that's exactly non-relativistic kinetic energy. So it works. In addition, if you couple this Hamiltonian to the external magnetic field, we learn from the gauge invariance that P is a derivative, has to be promoted to the covariant derivative. Because of gauge invariance. This is the covariant derivative. So what we talked about already like a month ago, I think, is that we need to have gauge invariance to make sure that the redundancy in vector potential doesn't affect physics. And you will make sure that your theory is gauge invariant. Every derivative has to be promoted to covariant derivative. And covariant derivative was defined to have this spatial derivative always accompanied by the vector potential. And time derivative is always accompanied by the scalar potential. So that's something we learned on the way. So here we are only interested in the magnetic field to understand the magnetic moment. So all we have to do is to promote this argument where P has to be replaced by P minus EA. So going back to the second line from below, and here we put in P minus EA. And then 2mc squared. And again, sigma P minus EA. And it doesn't seem to change much. We can still cancel these C's. It looks like you're going to get P squared over 2m. But here we have to be a little bit more careful in working out this times that. So what I told you just a minute ago is that sigma I, sigma j is delta ij plus I epsilon ijk sigma k. And when you work this product out, that's given by sigma I, sigma j, p minus ai, p minus ej. That's what this wavy line is supposed to be. And here we use this identity. And delta ij piece obviously becomes p minus ej squared. That's what you expected. But here's the additional piece. And I and j indices are antisymmetric here. So summing over I and j indices, this can be turned into a commutator because you're adding the same thing with I and j replaced with a negative sign at the expense of the factor of a half. And in the absence of the vector potential, Pi, Pj commutator, of course, is identically zero. We don't have to worry about it. That's how we end up getting just a P squared over 2m. But when you have the vector potential in it, vector potential depends on the position. P is the position derivative. They may not commute, so we have to be aware of this possible commutator. So this is P minus EA squared plus I 1/2 epsilon ijk, sigma k, p minus ea I, p minus ea j, and p is supposed to be derivative. So when p acts on minus ea, I get h bar over I, del I aj. When you look at the opposite order here, I get del j ai, but with relative minus sign because that's the other term in the commutator. And now you see that this is actually a magnetic field. And together with another epsilon in front, and when you sum of I and k indices, and to be avoid the classifications, you change to L. This I and j are summed with these I and j. So if I and j are, for example, 1, 2, I have 1, 2. And then k and L should be both 3 in that case. But in this sum, I also have 2, 1, 3, 2, 1, 3. So I'm adding the same thing twice. That cancels the factor of a half. So I get I, and k and L are the same. So k turns into L, and minus e h bar over I, dl. So i's cancel, minus e h bar sigma dot b. So I put this now back into the fourth line from below. Then the Hamiltonian turns into mc squared as the rest energy, and times 1 over 2m. That's the first term. But I also have the second term. And h bar sigma is 2s. So I can rewrite this as 2me s dot b. And here's the factor of 2. That's the G factor. So just by taking the non-relativistic limit of the Dirac equation, you can work out how this Dirac particle would couple to the magnetic field, and you do get this ordinary coupling of p minus ea squared over 2m, as you expect from gauge invariance. But in addition, you get the coupling of the spin to the magnetic field, which is of the form of the magnetic moment coupling. A magnetic moment in the unit of Bohr magneton turns out to be 2. That's the G factor of Dirac particle. And that's what you get to use, you get told to use for electron in atoms. Unless you use G factor of 2, you don't get the correct spectrum, for example, for the Zeeman effect. And G factor of 2 is not an input anymore, it's an output. That's something you can derive from the theory once you take this approach of Dirac equation. Now it starts to look even better, not just reproducing what we knew about the relativistic particle. We now have an extra prediction. The G factor has to be 2. And that's an incredible success, it turns out. And so far, this is an incredible successful theory where you do predict spin has to be 1/2, and that spin 1/2 particle should couple to the magnetic field with a G factor of 2. They're all outputs from the idea of trying to build this relativistic quantum mechanics. And so far, great. Not just so far so good, so far so great. So that's the idea originally by Dirac. But this is how far you can push. Now we come to the question whether this really works. and run into problems of what is called the negative energy solutions. And in the end, we have to go to quantum field theory. It turns out the relativistic quantum mechanics in the end fails. It just doesn't work. But before getting into this, any questions about this discussion? How to take non-relativistic limit? You can use the usual perturbation theory in quantum mechanics at the second order. In addition of getting usual p squared minus 2m as the kinetic energy, you would also predict the g factor of the spin 1/2 particle should be 2. Yes?
So sometimes people talk about like G minus 2.
Yeah, that's right. So what we know from experiments is that G factor is very close to 2, but there's a correction of the order of a per mil and below. And it turns out the G factor is not exactly 2. And that's something we will understand when we actually put the Dirac equation into QFT and talk about the high order perturbative corrections to it, and we'll come back and talk about that. So it turns out that G factor 2 is a prediction at the lowest order perturbation theory, but at the higher order perturbation theory, you do have the corrections to 2, and it turns out that's something you can compute, and it does agree with experiments only after you put in these corrections, which you can predict, and theory and experiments agree extremely well with each other. So we'll come back and talk about that. But anyway, so this corresponds to lowest order perturbation theory, and then prediction is that G factor is 2. Yes?
Would the corrections using this Dirac theory be the same?
That's what's it again, Jackie?
You mentioned there would be corrections to G equals 2.
Yeah, G.
I was asking if we went higher order in Dirac, would it also give similar correction?
Similar among what particle species you're talking about? Like comparing electron and muon?
No, you were saying the experimental value for G is different from 2.
Mm-hmm.
And it makes sense when we go into QFT and do the higher order.
Right. So the correction turns out to be only about the alpha over 2 pi. G minus 2 is only alpha over pi, turns out. 1 over 137 over pi, so that's like a 3 per mil. So 2.003, so that's a small correction. So starting with G factor 2 really doesn't make sense as a starting point for perturbation theory. Does that answer your question?
Yeah, my question was just if we did, because we only did first order perturbation using Dirac.
Uh-huh.
If we went to second order or third order, would it give
I see. Yeah, so if you go to higher order, then you get correction suppressed by 1 over c, but that doesn't give you the forward magnetic moment. So this perturbation theory is not the perturbation theory that will give you correction to G equal 2. But I can just draw a diagram because we did introduce the idea of the Feynman diagram. So electron comes in, emits a photon as a virtual state of the intermediate state in perturbation theory. It reabsorbs the photon and turns back into the electron while electron will interact with the magnetic field while it separates into this virtual state. That's the perturbative correction we have to compute when you go to QFT, and you can, and that precisely gives you this correction so that it agrees with the experiment. So that's not this perturbation in power series in P over MC, but rather a perturbation in the sense of this time-dependent perturbation theory as we talked about in QFT. Thank you for that question, Jackie. Any other questions? Okay, so far, great, right? But what is the problem? Rather than doing this perturbation in P of MC, let's just theorize this equation and go ahead and solve it. First, for a particle at rest, where momentum vanishes. When momentum vanishes, Hamiltonian is just mc squared beta. Beta, as we talked about, is 1 minus 1. And 1 in this case is the 2 by 3 matrix. Minus 1 is also true by unique matrix with over minus sign and psi. So you see four solutions. Psi being e to the minus I mc squared t over h bar, where energy is given by mc squared. That's the first component. You can also have a solution that looks like this, which also corresponds to the energy being mc squared. That makes sense. Relativistic particle at rest has the this rest energy of mc squared, so that's exactly what you get. In addition, you get two states like this. And as we talked about, spin is given by this h over 2 times sigma matrix. If you look at the z component, that's sigma sigma. For z component, this is 1 minus 1, that's sigma z. Also 1 minus 1, that's sigma z. So you see that these two solutions correspond to spin pointing in a positive z direction and spin pointing to a positive negative z direction. So this really corresponds to energy mc squared is the plus h over 2. And this one is energy mc squared, and spin is negative h over 2. Again, so far so good. That's exactly what you expect for spin 1/2 particle. If it's at rest, when p equals 0, energy is the rest energy of mc squared. You have two states, and they correspond to spin up and spin down. Again, so far so good. But now you start to see something strange. If you look at the bottom two components, mc squared is multiplied by minus 1. That looks like you have a solution whose energy is negative mc squared. You have a negative energy solution. So let's write that out too. Again, solving this equation is almost trivial. Plus energy is minus mc squared. Spin is up, plus 1. And the final solution for the lowest component, negative mc squared, is minus h over 2. Now, we have to make sense out of that. We find a solution whose energy is negative. So what do we do with this? And if there is such a negative energy particle, then if you actually go ahead and also talk about finite momentum, and as a function of momentum, energy is supposed to be mc squared plus cp squared. So that looks like this. And this is a solution we just obtained. When momentum vanishes, energy is plus mc squared. But when you go ahead and solve this, including finite momentum, you find negative energy solutions for all momenta. With the over minus sign, this is a solution we just obtained when p vanishes and energy is minus mc squared. So the spectrum of the Dirac equation looks like this, and you have these negative energy solutions. And that would be a problem, because suppose you have a single electron just moving in space, but that electron might decay into a negative energy electron by emitting a photon. You don't find a stable electron. That doesn't sound right. Is so far okay? No questions? But this is the point you might remember. Oops. That we have seen this type of problem before. When we talked about electrons in metal, Hamiltonian, including the chemical potential, looked like this. And we found the ground state for it. Namely that we filled all the states, this n, occupation number, and here it's 1, all the way to the Fermi momentum, which was given by the chemical potential. So then below this chemical potential, p squared of 2m minus mu was negative. So you had a negative energy solution here. But that was not a problem because that just tells you that you're supposed to occupy those states. And because energy is negative, by occupying it, you lower the energy. So when you're looking for the ground state, you better occupy all of those negative energy solutions to find the ground state, because occupying it buys you more energy. You can lower the energy. So you keep lowering the energy until you fill all of those negative energy states to hit the ground state. So that's something we have done before. So the idea here is that we have this negative energy solutions, but the idea is that you fill all of them. To find the ground state. In the Hamiltonian we just saw, there is no chemical potential in there, which means the chemical potential is actually at 0. Which means every state below the chemical potential, that's the Fermi energy, has to be occupied, which is precisely negative energy solutions, because chemical potential is 0, you occupy everything below it, and keep everything above the chemical potential vacant. They are not occupied, so these states are all open. That's the ground state. So these states are all unoccupied. These states are all occupied. If you remember what we have done with this, the electrons in metal, and if I actually do it plot in a different way, we have the energy p squared to m, yes, mu. In this picture, once you have this curve that p is p squared to m, corresponds to occupying all of these states below mu. That's its occupation number 1. And all those states up there are vacant. So that was the picture we had for electrons in metal. And we're doing the same thing, except that this line for the Fermi energy goes straight in between the positive energy solutions and negative energy solutions, so that we occupy all of these negative energy solutions. All the positive energy solutions are unoccupied. And once you're in this situation, electron, if you occupy this state over here, and if you worry that this electron might decay down to negative energy states by emitting a photon, it can, as long as this particle obeys Fermi statistics. This is already occupied, So this particle can decay to occupy the same state more than once. That's the Pauli's exclusion principle, which I argue should be now renamed diversity principle. And so this state is already occupied. So this doesn't happen. So now electron is stable. So that's what Dirac came up with. Then things seem to be consistent, but Dirac had to give up the original motivation for the whole thing. He wanted to come up with relativistic quantum mechanics for a single particle. Wave function psi was supposed to be a function of only one x and p, which was meant to describe a single particle. But it turns out that the Dirac equation doesn't allow you to talk about single particle problem. You have to talk about this multi-particle system, in particular, infinite particle system. And that's when we have to do the same thing we did with electrons in metal. So we use the language of QFT now, namely that all of the states the ground state is not the vacuum state anymore. Ground state is annihilated by the annihilation operator when P is bigger than the Fermi momentum. But rather the annihilation operator, ground state is annihilated by the creation operator when P is less than Fermi momentum. That's what we did. Then we have to use this language of creation-annihilation operator because now you're talking about multi-particle state, not a single particle state. And so your ground state is not a vacuum anymore. The same here. The ground state of the Dirac theory is not a vacuum state, but you have an infinite number of negative energy electrons occupied, and this is what is called the Dirac sea. So if you buy into this idea, what we think is nothing, the empty space out there, if you go on SpaceX, whatever the ship you can get on, how much do you have to pay for that? $10 million? I don't know. I really hope I can get it out of space myself, but I don't think I can ever afford it. But anyway, so if you think you have gone out to outer space where it's vacuum and nothing, it is actually supposed to be made of this infinite number of negative electrons out there. That's the idea of Dirac sea. Sounds crazy, but that's the only way of making sense out of the Dirac theory, it turns out. Okay, let me stop here. I'm sure there are questions about this. Yes?
What about the electron repulsion effect?
Again, I can't hear you.
If you have like an infinite number, then what about repulsion effect?
So that's an excellent question too. So once you occupy all of these negative energy electrons, it looks like the vacuum has infinite number of negative charge too. So the way we actually deal with this thing is that we say, okay, because the ground state already has infinite number of charges, the only thing we can make sense of it is when you add extra degrees of freedom, how much charge changes relative to the ground state. That is a physical question you can ask. So whenever you have this kind of infinite number of particles going on, and that defines the ground state, the only sensible question you can ask is how much does the feature of the ground state change when you have extra particles in it. If you add one more electron in here, you have added E to this infinite number of charges, but that difference is something you can measure. And so if you take that idea, then you can still make sense of the notion of electric charge, or energy, or angular momentum. Everything is measured relative to this ground state, and that quantity is well defined. That's the way we view this issue. So that sounds like a little cheating, maybe, but that's the way we make sense out of it. Yes?
So Dirac just said that the entire vacuum is full of charge, so was it change the concept of zero charge for like full sea of negative charge, we just pretend like there's lots of electrons everywhere?
That's right. So it turns out that, for example, there's something called strange notion, vacuum polarization. So when you apply electric field on vacuum, which is actually full of these negative energy electrons, all the electrons in the Dirac sea would move opposite to the electric field. They can't really move because all the states are occupied, but there is an effect that would give you polarization of the vacuum, which ends up, for example, when you place a external charge here, then the external charge would actually attract all of these negative energy electrons, so they get partially screened, just like placing a particle in a plasma. So that would actually make the charge look a little bit smaller. But if you look much more closely, when you actually measure the charge at the smaller distances, then you can take off the screening effect and look more closely at what the charge originally was. Then the charge should look a little bit bigger. And that effect had been observed. Namely, if you measure the charge of objects at different distance scales, which of course can be done at different momentum scale, namely you measure the charge in, let's say, quantum Hall effect, which is a very precise prediction so that you can measure the charge there at very low energies. But you can also try to measure the charge of electron in high energy collider experiments where smash electron and positron at energy of many billions of electron volts. Then you are measuring the electric charge by narrowing in on smaller distances, and you do find the charge is a little bit bigger. At a few tens of giga-electron volt, the charge actually changes. The alpha changes from 1/137 to 1/129. Not a big effect, but it's a measurable effect, even bigger than a few percent. And indeed, charge changes, which means the vacuum does polarize, and it really does happen. So talking about Dirac sea is not just academic exercise, it does have a physical impact, it turns out. And we normally don't talk about Dirac sea because once you actually do this in QFT, just like what we have done with this issue of the electrons in a hole, instead of talking about this as the creation operator, remember we defined annihilation operator of the hole instead. And once you switch to the language, you don't need to talk about this Dirac sea anymore. So the vacuum state is annihilated by annihilation operator of the particle and annihilation operator of the hole. And once again, if you remember the homework problem was the exact problem, that by using the language of the hole, you could figure out the quantum number of the atomic state, the 7A family and 3A family, by changing the sign of the electron to the opposite sign for the charge for the hole. So you do the same thing. And once you switch the language of the hole, the excitation you will talk about is the absence of the electron in the Dirac sea, which is obtained by annihilation operator of the electron. But once you switch the language of the hole, this is the creation operator of the hole instead of annihilation operator of the particle. And the hole then would have the opposite charge. If electron has negative E as its charge, this hole would have the charge positive E. It's given by the same mass. Now that you switch the sign of energy for the hole, that's what we did. You remember, once you actually write this in terms of hole, you switch this because A dagger turns into B, A turns into B dagger. If you do to switch the order to B dagger B, then that gives you minus sign from the anti-commutation relation. That will change the sign in a coefficient. So this becomes mu minus p squared over 2m, which is positive. Same way, this negative energy times A dagger A turns into positive energy, B dagger B, because A is B, A is B dagger, A dagger is B. You have to switch the order to make it into B dagger B, because it has to be fermion, they anti-commute, that gives you a minus sign. So this negative energy turns into positive energy. So you find energy given by that. That has the same mass in here as this mass over there. So now you conclude that this is really the particle-antiparticle. So this hole of charge plus E is the antiparticle. This is getting pretty busy, so let me the hole in Dirac C is the anti-particle of electron, which is the positron. So we introduced this idea of antimatter already when we talked about the Klein-Gordon equation, but this was the first time. The Klein-Gordon equation actually came later, historically. So this is the time when the prediction of antimatter first came out. And initially, Dirac didn't like that. You know, he didn't want to predict a new particle. And if he doesn't get discovered, of course, he will be proven wrong. That was not what he preferred. So he actually wanted to say, well, no, this theory predicts the positively charged particle, so maybe this is actually a proton instead. But of course, that doesn't work because his theory predicts this positively charged object have the same mass as the electron, so it doesn't work, but he sort of wanted to protect himself, right, from embarrassment. So this is what he argued. But the other people, like Wigner, said, no, Paul, you're wrong. You know, this can't possibly be proton because it has the same mass as the electron. This has to be a genuinely new particle. You are predicting that there's a new particle out there we haven't seen yet. And a few years later, it was discovered. So Anderson from Caltech had this cloud chamber. And when a charged particle goes through, there's this oversaturated cloud, which is transparent at the beginning. But when charged particle comes in here, because the state is oversaturated, it quickly ionizes the electron in its way, and that will give you the cloud gathering around it. So that's how you actually end up seeing a track of charged particle going through. That's the cloud chamber. And he exposed his cloud chamber to cosmic rays. And if there's some charged particle going through, he can see it. And one thing he was very clever about is that, first of all, he applied magnetic field so that these particles bend its trajectory if it's charged. And which way it bends tell you what is the charge of the particle. You can even measure the momentum by the curvature radius of the charge track. That's the principle we still use in accelerated experiments today. But if that's the only thing there is, you can tell if it's the negative charged particle going this way or positive charged particle going the other way, because the track looks the same. So in addition to this magnetic field, he actually put in a steel plate in the middle of it. And what he saw was like this. So here you see a slightly curved charge track. And after passing through the steel plate, it starts to curl more, which means that above the steel plate, you have momentum less than the momentum below the steel plate, because the only thing the steel plate can do is let the particle lose momentum. It doesn't pick up momentum. So by looking at the shape of the curvature of the tracks, he could tell the particle actually went from this direction rather than that direction. And if he knows that this came from this direction, by looking at the curvature of the track, he could tell that this is actually a positively charged particle, not negatively charged particle that came from above, but positively charged particle that came from below in this picture. So this has to be a positively charged particle. And he can even see the level of ionization in it, and also looking at the curvature of the track that gives you the information on momentum, he could conclude that this particle has about the same mass as the electron. He wasn't very accurate by the single event. He had only single event in cloud chamber. And then wrote the paper called Positive Electron. Just one event in cloud chamber, in addition to the magnetic field, I don't know if he intended for this purpose, but there was a steel plate going through the cloud chamber for some reason, and that allowed him to tell the particle went from one direction than the other. Looking at the curvature, he could tell the charge, and that was the positive electron. And that was the title of the paper that of course earned him a Nobel Prize, first discovery of antimatter. So that is a discovery of positron. If I remember correctly, that's 1932 or 3, I forgot. All right, any questions about this? Yes?
I want to ask about the energy ladder, because the Dirac seems very asymmetric to me. Why don't we just view the upper part of the energy ladder to be another Dirac sea, which is occupied by positrons?
Yeah.
So this explains better when we go into the vacuum polarization, because we can see that the vacuum is two parts of Dirac sea overlap together. So if an electro field added on the vacuum, then the positron electron just spread out and to form a polarization.
Yeah, indeed. So it's not quite exactly what you suggested, but something similar. Once you actually go to QFD, so right now we are still trying to stick with the single particle group description as much as we can push, right? But once you decide, well, this has to be QFD now, then you don't have to talk about this Dirac sea anymore. And let me give you the upshot. We can come back and talk about it in more detail later. So just like in the case of this chemical potential, Hamiltonian ends up being over momentum spin now. And this, of course, comes with the spin index. And then we have this negative energy solution. But using the language of the whole, I write this as, I don't know, maybe C. So instead of creation operator for the negative energy electron, you introduce the annihilation operator of the whole, whose momentum is minus p because that's the absence of p. Spin is also minus s because that's the absence of spin. And then annihilation operator turns into creation operator. If you do that, you switch the order between C and C dagger by using anti-commutation relation because it's a fermion. And when you change the order between annihilation and creation operator, I have minus S dagger minus B. But this minus sign now changes to plus sign. Then we know what the ground state of this Hamiltonian is. Namely, it is annihilated both by A, annihilation operator, and C, annihilation operator. And that's the ground state. We have done that with the electrons in the metal, but now we are applying this idea to our universe now. And then you don't have to speak about Dirac C anymore. The ground state is simply defined by a state that is annihilated by annihilation operator, because there's no particle nor hole or antimatter. Ground state is a state that doesn't have electron or positron in it. Then treatment is symmetric between particle and antiparticle. That's what you are after. You don't have to speak of Dirac C anymore. And the ground state of this Hamiltonian is now well defined. And that's it. And once you define the ground state this way, for example, if there's a hole here, the electron here can decay into this hole and emit photon. To conserve energy momentum, it turns out at least you need to emit 2 photons instead of 1. But that process is now understood as a pair annihilation of electron and positron coming together and annihilate into 2 gammas. So instead of talking about the particle decaying into the hole, you can talk about particle and antiparticle annihilating with each other. And that's what we talked about already in the case of Klein-Gordon equation. So that's how the particle and antiparticle can really annihilate with each other. And that's something we can actually observe in experiments. So the idea is that, this was a long discussion, but Dirac initially wanted to come up with the relativistic quantum mechanics. And he got pretty close. He got a good equation. It's relativistic. It reproduces energy of the correct expression, mcc squared plus cp squared square root. He could predict that that particle is spin 1/2. He could even predict the G factor of that particle. That came out correctly to be 2. So far so good. But because of this negative energy solution, in the end, he had to abandon the idea that this was a single particle quantum mechanics. It had to be field theory. So his equation was right, but interpretation was wrong. Namely that Dirac equation was supposed to be an equation for quantum field theory instead of quantum mechanics. Once this is a quantum field theory, you have a well-defined way of defining the ground state of the quantum field theory, which corresponds to occupying all of its negative energy solutions. But QFT is more clever than that, because by switching the idea of creation and annihilation operator, then you can define a hole, which is antiparticle in this case. And ground state is a state where simply you don't have any particles nor antiparticles. A well-defined ground state. And on top of this ground state, you can create particle and antiparticle. That's again well-defined state. Then you can observe how a particle and antiparticle can annihilate with each other. And for this purpose, we have to put in the interaction to the electromagnetism, and that is what we do when we actually build up the quantum electromagnetism, or QED, starting next week. Then you can even compute this kind of process, how electron and positron would annihilate into a pair of photons. Then everything turns out to be a consistent theory. So that, in the end, turned out to be the right idea. So somehow, totally wrong motivation led him to discover the right equation, and that actually the way we now understand spin 1/2 particles in the framework of quantum field theory. Yes?
But if we can, from this point of view, we can see the positron and the electron, they're very symmetric. And,
Right.
If we treat these two antimatters as equal footing, unequal footing, can we see why there is asymmetry in reality? Because we view electrons more often, and we will see much of the positrons. And it is this asymmetry that keep us alive. And
That's
it's just
a $1 trillion question. So if we treat matter and antimatter equally this way, how come that there's only matter around us? And if the universe indeed does have the symmetry between matter and antimatter, there has to be antimatter around you, and that would be a very dangerous world to live in. Because the minute you touch antimatter, you annihilate it. But part of you also annihilate together with it, and it's dangerous. And as far as how the antimatter might look, you only change the sign of the charge, mass is the same. So if there's an ice cream made of antimatter, if you look at it, it will look exactly the same. Because by looking at it, the only thing you're doing is to exchange photons. And photon only interact with the charge, no matter what the size of the charge is. So you can't tell if it's matter or antimatter. So it looks like exactly the same ice cream. But the minute you grab it, your hand is made of matter, ice cream is made of antimatter, they start to annihilate with each other. There will be a huge explosion. And it turns out that there's actually a movie called that's novel originally by Dan Brown, Angels and Demons. And in that movie, the antimatter shows up. And some scientists at CERN, according to that novel, managed to produce a quarter gram of antimatter without the knowledge of the director general. I don't think it was Fabio Giannoli back then, but anyway, so that was the beginning of the novel. And this falls into the wrong hands. And you may think this is nothing, quarter gram, it's like a sugar cube, right? But if you have this much mc squared, and if this falls on the ground, which is made of matter, and same amount of quarter gram would annihilate together with it, and total energy released by this much mc squared, you're a physicist so you can compute this, turns out to be about the same energy of atomic bomb in Hiroshima. Because mc squared is a big number. We normally can't make use of it. We burn stuff where the only energy you release is that basically excitation energy of the electrons inside chemical compounds. That's what fuels the electron volt. But same electron, if I annihilate the positron, would release million electron volt. So that's million times bigger energy. So quarter gram is equivalent to an atomic bomb. And that was the threat these bad guys would actually pose to the Pope in Vatican, and that's how the movie goes. The incredible part of this movie is that when the scientists created this quarter gram of antimatter, the director general didn't notice it. But to produce this much antimatter, you need to put in a lot of power into the accelerator. And somebody estimated the cost of the power consumption. That turned out to be, if I remember correctly, like $1 trillion. Because you have to make a lot of energy to create antimatter, because that is equivalent to energy of atomic bomb. So if you spend that much money in your experiment, and if the director general doesn't notice it, that means that laboratory has a huge budget. So I really am jealous of that. But anyway, so we seem to have this issue why we are living in a safe world where we don't have to worry about getting annihilated by antimatter constantly. And that's one of the biggest questions in modern cosmology. Somehow, Big Bang started out the universe, and George Smoot saw Big Bang. You can take a picture of it, so it was really true. And so there was a huge amount of energy. When energy turns into matter and antimatter, as we're talking about, you can send in energy and create matter and antimatter, but always one-to-one. So Big Bang turned energy into the same amount of matter and antimatter. And if it stayed that way, eventually they meet and they will annihilate, and then you wouldn't be here. What should have happened is that after the Big Bang, somehow one piece of antimatter got turned into matter. Nobody knows how, nobody knows when, but this is what must have happened. And this is a tiny effect. This is like 1 out of billion. And this one turned into matter, so this is now 2. And then when they meet, they all annihilate with each other, except for this 2, and that's you guys. That's what we think now. How exactly this happened is one of the biggest mysteries in modern cosmology, and a lot of people are trying to understand this, so whenever I have some extra time, I will talk about that. But let me leave it that way. For some reason, our universe is asymmetric. This is matter, antimatter, asymmetry. For some reason, our universe is asymmetric between matter and antimatter. So as I said, how that happened, nobody knows. And that's why a lot of research is actually going into this, also in our department. And so let me mention this sometime later, but that's a very good question, and that's still not understood. Okay, any other questions? All right, so we continue on with the Dirac theory, now in view of QFT instead of single particle quantum mechanics. And not only that, we have this solution as the rest, we would like to also work out solution at motion, non-zero momentum explicitly, and then start doing some computation with it. All right? Oh, and as I announced by the B courses, today I have a conflict for the office hour with the faculty meeting, and hopefully faculty meeting is over before 5. So whenever I become available, I send an email to the B courses, and then you can either Zoom in or come to my office.